This is lecture number 11 of the Control Systems course, and I'm your instructor, Rizwan Azam. So in the previous few lectures, you have studied the mathematical modeling of electrical networks and also the mechanical networks. In this lecture, we will study how to model a system which is the hybrid of electrical and mechanical components, and we call this kind of systems electromechanical systems. In this lecture, we will deal with a particular type of electromechanical system, which is a motor. We know that a motor is an electromechanical component that takes voltage as input and gives displacement as the output. So in this lecture, we will derive the transfer function for a simple armature controlled DC motor. In the figure A, we can see we have two portions of the motor. First portion is the rotatory part, which is on the left, and the second portion is the stationary part, which is on the right. The stationary part produces magnetic field, and that can be produced by permanent magnets as well as electromagnets. And this part is called the fixed field. The second part is the rotating part, and that is called the armature. We have to find the transfer function g of s for this kind of motor, where the input of this transfer function will be the applied voltage EA, and the output will be the angular displacement theta m, as shown in the figure B. We will study the components and all the currents and voltages of the motor in more detail in the next slide. The basic working principle of a motor is that if we have some magnetic field like this one, and we place a coil like this one, and we apply a voltage at the ends of the coil, then there will be a current which flows through the coil due to the current which passes through the conductor and the magnetic field around it. The conductor will feel some force and hence a torque which will rotate the coil. In the case of DC motor, the current through the armature is IA, the armature current, and the applied voltage are EA, the armature terminal voltage. Tm is the motor torque, and due to this torque, the motor rotates with the speed of theta m in radians per seconds. So whenever a coil rotates in the magnetic field, then according to the Faraday's law, there will be some voltages produced in the coil, which is called the back EMF, VB. And apart from them, we have RA, the armature resistance, and LA, the armature inductance. To find the transfer function of the DC motor, we will firstly find the expression for the back EMF. Since the current carrying conductor is rotating in the magnetic field, then its voltage will be proportional to the speed of the rotation. Hence, the back EMF is equal to Kb times theta m dot, where the Kb is constant of proportionality, and this is also called the back EMF constant. Theta m dot, or d theta m by dt, can also be called the angular velocity omega m of t. So if we take the Laplace transform of above equation, we will have this equation. So if we convert the previous armature circuit into its equivalent Laplace transform circuit and apply the KVL, or the Kirchhoff's voltage law, then we will have this equation, where RAIA is the voltage across the armature resistance. LASIA is the voltage across the conductor, or LA. VB is the back EMF voltage, and EA is the applied voltage. The torque Tm produced by the motor is directly proportional to the armature current Ia. Hence, the relationship between torque and current can be written by this equation. Kt is the motor torque constant, and usually it depends on the motor and magnetic field characteristics. So if we rearrange the above equation, we can write the equation in this form. And if we put the expression of Ia in the above equation, we get the following equation. Now, if we see this equation, the objective was to find the transfer function between EA and theta m. But we can see that we have another function which is Tm as well. So we have to remove this Tm and we have to write this Tm in the terms of theta m. To find the relationship between the torque and the angular displacement theta m, we will consider a typical equivalent mechanical load of a motor. And generally this load consists of two parts. One is the inertia and the second one is the damper. Now this inertia is the combination of, this is basically the equivalent inertia, and it is the combination of armature inertia and as well as the inertia at the load side. Similarly, the damper is also the combination of the damper at the armature side and as well as the damper at the load side. So if we convert this load into its equivalent Laplace domain and write it into an equation form, we can get this equation easily. And if we substitute the relationship between Tm and theta m in the previous equation, we will get this equation. Now we can see that this whole equation is in terms of Ea and theta m. So from here we can easily find the relationship between Ea and theta m, which will be the transfer function of the motor. Firstly, we will take theta m common, and from there we can easily find the transfer function theta m divided by Ea. In the case of DC motor, usually the armature resistance is much larger than the armature inductance. Ra is much greater than La. Hence the terms with La can be ignored to simplify our calculations. So we can remove this term. And after taking the theta m from here and here common, we are left with this equation, and from here we can easily find the transfer function, which is theta m divided by Ea, written here. Now this transfer function looks difficult, but if you see it closely, basically we have some constants like Kt, Ra, Jm, Kb, Dm, etc. We have some electrical constants like Kt and Kb, Ra, etc. And we have also some mechanical constants which are Jm and Dm, etc. We can find these constants once we have some information about the load and the motor characteristics. So let's suppose we have the values of these constants. The final form of this transfer function will be much simpler than we have the form here. This will be just some constant divided by s into s plus another constant a. If we look at this transfer function closely, the motor transfer function has two poles, one at s equals to 0 and the other at s equals to minus a, and there are no zeros for this transfer function. So once again, The K and the A are some constant values depending upon the motor coefficients or constants. In the next few slides, we will see how to find these motor constants. So let us firstly discuss how to find the mechanical constants Jm and Dm. For that, we will take a DC motor which is driving a rotational mechanical load with the inertia Jl and the damper Dl. The motor itself has the inertia as Ja and the damper of the armature is dA. The inertia and the damper of the load can be reflected back to the armature of the motor so that they can be combined with the armature's inertia and the damper, and which will be equivalent to the total inertia and the total damper Jm and Dm respectively. So if we include the gears, then we can reflect back JL through this term and DL through this term. And at the armature side, the Jm will be the combination of armature's inertia and the inertia of the load, which is reflected back from the load to the armature. And similarly, the Dm will be the combination of the damper of the armature and the damper term which was reflected back from the load side. The electrical constants can be obtained by a dynamometer test in which we apply a constant voltage to the motor and the dynamometer measures the torque and speed of a motor. So as we have already considered La to be 0, so put La equals to 0 into the original equation before putting the value of Tm. So we will get this equation. To understand this equation in more detail, we have to transform this equation back to the time domain. So if we take the inverse Laplace of this equation, we will get its equivalent time domain expression written here. When the motor is being driven at a fixed voltage, then we will have a constant torque Tm and a constant speed of the motor omega m. That's why we have removed the dependency of the time with these two variables. And by the way, this omega m is nothing but the time derivative of the angular displacement theta m. From here, if we solve for Tm, we will get this expression for the torque. If we look at this equation closely, this is an equation of a line. If you remember y equals to mx plus c form, then this is the m, the slope of this line, and this is c, the intercept or the y-axis intercept of this line. For different values of EA, we will have different lines, and we can draw them together on a plot called the torque speed curve. On this particular torque speed curve, we have drawn two different lines for the two values of applied voltage EA1 and EA2. Similarly, we can have more of these lines on this curve. And we can see from here that the vertical axis is the torque axis and the horizontal axis is the speed axis. If we want to find the y-axis intercept, this point or this point, this will be when omega m equals to 0 at this point, omega m equals to 0. So if we put omega m equals to 0 in above equation, I will remove these writings from here. So if we put omega m equals to 0 in above equation, this term will be removed and we will be left with just kt divided by Ra into Ea on the right side. And on the left side, this Tm is called the T stall. So once again, when omega m equals to 0 is put in this equation, we will have the equation for the T stall. And also, when the torque is 0, the point where the line touches the horizontal axis is called the no-load speed of the motor. So if we put Tm equals to 0 in this equation, Tm will be cancelled out and we will be left with minus Kb Kt divided by Ra into omega m. And this omega m is, by the way, now omega no load. We can replace it by omega no load notation, and this will be equal to Kt by Ra into Ea. I have no space, so I am writing here Ea. Now Kt by Ra will be cancelled out on the both sides, and we are left with what? And by the way, there is no negative sign. This is now on the other side, so this is positive. Now we'll be left with Kb into omega no load equals to Ea. And from here we can find the expression for omega no load written here. So now these are two equations for T stall and no load speed. From these two expressions we can find the electrical constants of our interest, which were Kt by Ra, and we can find Kt by Ra from the first equation, and the final expression for Kt by Ra is written here. And from the second equation we can find the expression for Kb, and the expression for Kb is written here. So now we know how to find the mechanical constants as well as the electrical constants for the motor transfer function. Let's perform an example where we have to find the motor transfer function theta L by Ea, and we are given with the following schematic and the torque speed curve. So if we look the schematic closely, Ra is the armature resistance, and here we have taken La equals to 0. We are given with the armature inertia and the armature viscous damper. We know the gear ratio, and also we have the load inertia and load viscous damper available. In the figure B, we have a torque speed curve. We have T stall, we have the omega no load, and we are given with the value of the voltage on which the motor is operating. So from the schematic on the left side, we can find the mechanical components, and from the torque speed curve on the right side, we can find the electrical constants. We have already seen that the Jm equals to Ja plus Jl into N1 divided by N2 whole square. So we will just put the values of Ja, Jl, N1 and N2 here. And similarly, we can also find the Dm, which is dA plus dL n1 divided by n2 whole square. So by putting the values, we have found Jm to be 12 and Dm to be 10. Now to find the electrical constants, we will take help from the torque speed curve. If you remember from the previous discussion, the Kt divided by Ra was equal to T stall divided by Ea. So we already know T stall, which is 500, and we know Ea equals to 100. Hence, the Kt divided by Ra will be equal to just 5. Similarly, we can find the Kb from the expression Kb equals to Ea divided by omega no load. And we know that Ea is 100 and omega no load is 50. So the Kb will be just 2. So now we have the mechanical constants here and the electrical constants written here. We can plug these constants in this equation. So let's plug these constant in this equation in the next slide. So let me write down the found constants again. Jm was found to be 12 and Dm was found to be 10. Kt divided by Ra was found to be 5 and Kb was found to be 2. So let's put these constants in this expression. We will have theta m divided by Ea, that will be equal to, so Kt by Ra is 5 times 1 by Jm, and Jm is 12, so 5 divided by Jm divided by S plus 1 divided by Jm is 12 and Dm is 10 plus Kt by Ra is 5 times Kb is 2, so 10. So we can write, we can replace this Jm by just 12. So after some manipulations, the final transfer function theta m of S divided by Ea S will be 0.417 divided by S into S plus 1.667. So we have found the theta m divided by Ea, but if you read the statement of the question closely, we were actually asked to find theta L divided by Ea. Now the question will be, how do we find theta L divided by Ea? We don't know the expression for theta L divided by Ea. But actually, there is a relationship between theta L and theta M. We know that theta L and theta M are directly related through the turns ratio, and theta L divided by theta M is actually equal to N1 divided by N2. So from here we can find the relationship between theta L, which is 100, and N1 is 100 and 2 is 1000, multiplied by theta M. So this will be 1 by 10 theta M, or theta M by 1 by 10 theta M. So if we multiply 1 by 10 on both sides, we can have the transfer function theta L divided by theta A, which was the required transfer function. In summary, when we have to find the transfer function for a DC motor, we can use this expression, and the electrical and mechanical constants being used in this expression can be found in the similar fashion we have used in this example. So this concludes our discussion on the modeling of electromechanical systems.